So first, thank you all for coming to our presentation. It's going to be a real pleasure having you here. My name is Matthew Mummert, and we are Team E-Cubed. And the Team E-Cubed stands for the Electrical Engineering Experience. And the reason why we named our team that is because we have no computer engineers on our team at all. We're all electricals. And I want to introduce my team. This is Nick, our project manager. This is Eric, and then beyond him, there's Dave, and at the end, there's Ed. And I'm going to pass it on to Nick, who's going to talk about what it is that a micromouse actually is.
All right, so let's ask ourselves a question. What is Micromouse? Micromouse is a long-standing competition where we build an autonomous maze-solving robot that needs to find the center of a maze. Some of the maze specifications are: the maze consists of 16 by 16 cells. A cell is 18 centimeters by 18 centimeters. The walls are 5 centimeters high and 1.2 centimeters thick. And pretty much the mouse, you have 10 minutes for the mouse to map the maze. And as long as the mouse finds the center of the maze, that is your time, and the fastest mouse to the center of the maze wins. So the real question is, how do we reach the center? So I'm going to pass it off to Eric. He's going to talk about the intelligence.
Well, so how do we get to the center of the maze? Well, first and foremost, we have to know what a maze is. So the basic element of any maze is the cell. And here we have a list of the 16 possible configurations of cell walls. 16 is a special number for computer science. It means that we could represent any of these configurations with simply just four bits. Now what the bits mean is just the presence or the absence of a wall. So here's an example. The E-Cube mouse, our mouse, does not only learns walls, but it maintains this information too. It maintains cell addresses and a distance value. Now what are distance values? Distance values are the most important value for our algorithm. The distance value is the number of cells it takes for that cell to get to goal. For the flood fill algorithm that we're going to be using, that value is going to be updated. So here's how flood fill works. This is a demonstration, a simplified demonstration of a 5x5 maze. The grayed out walls are the ones that the mouse has yet to discover. The dark walls are the ones that the mouse already knows. The red square in the center is the goal. So how flood fill works is just a series of questions that the mouse asks itself. Are you in the goal? Could you move forward? Are there walls? And do the distance values need updating? After it answers all those questions, it proceeds to a cell of a lesser distance value. The E-Cube mouse that we have uses a modified version by inserting these two questions into there. Have I been here before? And what quadrant am I in? So as we run the simulation of this mouse running through the maze, it's going to proceed to cell values that are lesser distance values. At this position, he has two cells that are equal value, so that's why the quadrant question comes into play. Instead of, it'll come up to the decision to make an upward turn instead of a rightward turn. Once it enters that cell, it'll discover that wall using the sensor reading, and then proceed to here. Once it comes to here, now the mouse needs to update these values because they're consistent with the wall layout. These are no longer 3 cells away from the goal. So our algorithm will spit that out as 5 and 4, indicating the proper distance values of the cell. Now in order to perform all of this, the following functions need to orchestrate together as one. The scan for walls, to move mouse, set wall, and update distance values. Now this is an orchestration of all our hardware, and so here is Nick, who's going to give us an overview of the hardware.
All right, so here's a general overview of the 4 main components that makes our micromouse move. We have the eyes, which are the position sensors, the feet, which are the motors and the coders, the brains, which is the software, and the power is the energy spent by the mouse. So here's a general block diagram of our mouse. We have a 7.4 volt battery that feeds a 3.3 volt regulator, which feeds the discovery board, the MCU we were using. We have user interface buttons, As you see, the MCU tells the emitters to turn on, which are the eyes, and the pin diodes receive the light and feed the information back to the MCU. We have our motor controller, our H-bridge, which tells our motors to move and to speed up and slow down. And the motors feed the encoders, which gives information back to the MCU. So, speaking of the eyes of our mouse, here is Edward to talk about the sensors.
Sensors that are in our micromouse will detect the walls within the maze itself. As you can see here, the video we have, as the mouse travels throughout the maze, it will detect how close a wall actually is. Depending on that distance, our voltage will regulate. Yes, video is not playing. So, with that information, so as soon as the mouse turns on, it will spit out a light. That light will bounce off the wall, and we will receive that information. That information is then stored into ADC, and with that information, we are able to use our motors and gears. Right here is a lookup table what we have for our sensors. With that, we are able to navigate throughout the maze. And now with that, here's
All right, motors and encoders. The motors that we chose for our micro mouse are 30-to-1 gear ratio, low current brush DC motors. These specifications of these motors, one of the things that we needed for it was on the back side of the motor, we needed an extended shaft. That shaft holds our encoder plate, which runs through an optical interrupter. As the plate interrupts and allows the beam to pass, we get relatively a DC output from rail to rail from our encoders, which we use to navigate the main. Anyways, an encoder is a device that converts information from one format or code to another, and that's exactly what we're doing with our encoder. We take the speed as well as the distance traveled by adding up the actual ticks from our encoder and use that to help us move throughout the maze. What we ended up doing with our encoders is putting a plate on there that has flags rather than the initial design, which was with holes in it. What we determined is that flags make it so that the on and off time of the output from our encoder equal, which is nice because then we're not limited by any one factor. We do have a video. Oh, there it's going to play. This is a video of our actual encoders running through the optical sensors. That's them interrupting and then allowing the pass, or the beam to pass. Go ahead and hand it off, talk about power distribution.
All right, so our power distribution for our mouse. As you can see here, we have a lithium polymer battery. That's a 2-cell battery with a 260 milliamp per hour output. It also outputs 7.4 volts, and the dimensions are small enough to meet the specifications of our mouse. Also, we're using a surface mount voltage regulator. With the regulator, we were able to get an output voltage of 3.3 volts, which feeds a lot of our hardware. So it's within spec for our mouse. And here's Matt, he's going to talk about some software.
All right, so we have some sensors on our mouse. We have the wheel encoders, we have the distance sensors on the walls, and how do we actually use those sensors in software? So first let's talk about the wheel encoders. So basically, the wheel encoders give us a variable frequency input that we can take, and that frequency varies depending on how fast the wheel is actually turning. So we're able to take this frequency and we know how fast the wheel is turning, therefore we're able to look at both wheels to see how fast both of those wheels are turning and design a control system which keeps them both turning the same speed, which means the mouse is moving directly forward in a straight line. Next slide. And so you might ask, okay, well, how do we actually control the speed of the motors now that we know how fast they're turning? We can't exactly take the 7.3 volt battery and just, up and down the voltage as we please. So we use a technique called pulse width modulation. And what that is we're basically switching the power on and off in controlled bursts so we can control the speed of the motor. And by controlling the width of these pulses, we can control how much current flows to the motor and therefore the motor's speed. Next slide. And also, I want to briefly mention how we avoid colliding with walls using our distance sensors. And so basically, if the left wall is a little bit too close, then we're going to make the speed of the right, we're going to make the right wheel turn slower. And then if the right wall is too close, we're going to make the right wheel turn faster. And here's, this video shows an initial stab at this. You notice how it kind of swerves to avoid the wall? That was one of our first attempts at implementing this algorithm. And it does a really good job of showing how it swerves to implement the wall. All right, and next I'm going to turn it over to Nick again, who's going to talk about our finances and our project planning.
Okay, so our financial output at the end of the semester, we met the IEEE standard $500 budget instead of the SDSU $600 budget. Basically, we wanted to stay in spec with the IEEE contest regulations. So, as you can see here, our motors and our motor controllers cost the most. We also had a pretty large replacement part budget due to burning out LEDs and also H-bridges, which are our motor controllers. So our milestones we set for ourselves, this is our hardware section. We were pretty close to meeting our hardware milestones. We fell a little bit behind, but we were able to catch up. However, we ran into a lot of troubleshooting and problems, so we did catch up on our hardware section. In our software section, we're pretty close to meeting our self-made milestones. And we're right on track for Senior Design Day, which is Friday. So, on that note, Matt's going to talk a little bit about the conclusion.
Okay, so our hardware section took a little bit longer than expected. We had some kinks in the hardware we had to work out, but we got those worked out, and everything's working great on that side. The wheel encoders do a fantastic job of helping us keep track of how fast our mouse is moving, and therefore, with dead reckoning, how far we've gone. And the maze solving algorithm that we're using, the flood fill algorithm, is a very well understood algorithm. It's well developed, and the academic community has used it on many occasions. We're within budget, and our software section is just about complete for design day, and we're right on track. And thank you very much for coming to our presentation. And here's a little video of the mouse zipping through the maze. There it goes.